4 guys up to the board all at once, okay? And one guy is going to do CH4 at 273. Another guy is going to do CH4 at 546. Another guy is going to do N2 at 273. And another guy is going to do N2 at 546. So you notice I've confined you in space, so that's all the space you got. So you got to kind of plan out what you got to do. All right. So let's see. So here's the guys here, and let's not get bogged down in this because this is a pretty simple one. So first one's for Nick Nicolo, second one Matt Berry, third one Matt Bauer, the last one Nick Wetzel. So we got Matt and Nick and Nick. Now they're doing CH4 and CH4 and N2 and N2. Just as an observation.
Trippy.
It is a little bit. So
When do you leave?
What?
When do you leave?
Friday morning.
I talked to Mr. Alexa about taking Thomas Young's spot, but he wouldn't let me.
Tyler's still out.
And the yeah.
Also, you're a first year right? Stowe is.
Jacob Everson absent.
Yo, like if I just go straight down, I won't hit anything.
Yeah, this is a problem to do right now.
Did Wetzel go last year?
No. They're also like the worst last year.
Oh, was it?
Yeah, remember?
Yeah, that's the other thing.
Stop looking at me, bro. You're making me so uncomfortable. Quit looking at me, right?
So then give us a verb.
Looking at me, please.
I'm actually looking at that box behind you.
Are you going to the game tonight?
Really?
You have the school spirit.
What time is it?
It's an orange out and you're wearing black.
What time is it? It's orange out and you're wearing white.
I'm wearing black.
Something.
Wait, what time is that?
Game?
Yeah, after the yeah. But if it didn't know, then you no, that's just for direct. And then if it's interaction, then for interaction, then for both. No way.
So this is how we
We want to go look at it.
I only came out with boy.
Trying to help you.
I only came out with trying to help you.
You gotta get a track.
Not so cheap. That's what I'm gonna share the side to walk.
They're like completely bold.
Yeah, that's so shave it and then just go right on. It's so
Look like a horse. There you go.
Yeah.
Gary, you want to be you want to begin?
we can take John to pack some sandwiches. No, we can make yeah. Do you know James' address? Should come out and hey, it'll be after base. Oh, it's a printer.
Yeah, yo, dude, you know where John Evans lives?
Hang on.
It's going to come out meters per second. It's going to go down to meters per second squared underneath the bracket or underneath the square root. So yes.
Yeah. Remember where that guy got shot?
Yeah.
And then there's the bridge over that like ravine road. Yeah, you go over that and then it's kind of near there.
Oh, the fugitive dude.
Yeah, dude.
The one that's running from Cleveland or whatever.
Yeah, that was like insanely close to my place.
Really?
It's like 2 blocks.
Were you on lockdown?
Yeah. I was at school.
Try that. If you multiply and you get numbers under, so you got 3. Divide them.
I can't take you home.
It should be about the same thing. No, you take this, divide by this, or this. Okay. Whatever you do to one,
That's why, and then the next one, she gives you the and she gives you everything. You just have to know how to use it.
Does he charge those? Why are they dividing it? 100? Where?
You're right.
That's what I did.
And it's by 1,000. So that's about this kilograms.
Mr. Markley, how do you get the square root?
You're gonna see mine? I'm gonna go. How many people do you have? So you have more people. About quiz it. Quiz it. Make a quiz. I have two sets. For this? You're not at the same level as me. You give me a quiz on this.
Go sit down and memorize your own phone.
Oh, I can do that.
Where's this skip? That up 4 500.
No, that's the thing we have to write down.
Would you know what formula?
Yo, dude.
What type of problem?
Dude, they're 5 formulas.
You have to get like 2.
Real though.
One for partial pressure, one for tide, one for average kinetic energy, one for mu RMS, and one for fusion rate.
Mr. Martin, I know it's meters per second, but I don't know why it's meters per second.
Okay, so we tracked units before like this. We did this in class. We said this is the units are R is joules per Kelvin mole. We said that T is temperature, so that's Kelvin. And we said that's all over kilograms per mole. Okay, that's all the units, okay? So if I expand out joule into kilogram, meter squared per second squared, times Kelvin over kilograms per mole. Those are all my units, okay? Oh, I'm sorry, this is joules per Kelvin mole. That's joules per Kelvin mole. Okay, times Kelvin. You good there?
Yeah, it's just another way to say
Joules is, yeah, kilograms meter squared per second squared. I got Kelvin mole in the bottom, so I put Kelvin mole in the bottom. There's that K, kilogram and mole. So we could say K and K cancel, mole and mole cancel, kilogram and kilogram cancel, and that leaves me meter squared per second squared. And when I take the square root, you get meters per second. So if you can track units, great, but if you can't, you just memorize that's the units. Okay, so we look at these solutions here. They all look pretty reasonable. So first thing is let's compare apples to apples. Let's compare CH4 to CH4. Well, when it's at this temperature and then at a higher temperature, it's going slower and then faster. That makes sense. When this is at a lower temperature and a higher temperature, this is going slower, this is going faster. Now again, apples and apples. Let's say we compare CH4 at 273 to N2 at 273. The CH4 is going faster than the N2. Why? The CH4
It's lighter.
is lighter, has less mass, so it has to go faster to get the same kinetic energy. And again, compare the 546s. This one is moving, whoa, got a problem here. This says that this one is going 922, and this one isn't going faster, and it should be. I'm sorry, I take that back. What am I talking about? This is going faster, this is going slower at the same temperature. That should be going faster because it is lighter. I don't know where my brain went on that. Okay, so we good on that?
Yeah.
So even though the temperature's doubled, it won't always double the velocity.
Correct. It doubles the energy, but not the velocity. And the reason is, you want to know, kinetic energy is 1/2 mass times velocity squared. Okay. So when we talk about, like we said, when we double the temperature, we double the kinetic energy, okay? Well, that's because velocity plays a bigger role. It's squared. You get what I'm saying?
Yeah.
Everybody see what I'm saying there? Mathematically speaking? Okay, so if you get that, cool. If you don't, it's not a big deal.
Goes
Right?
exponentially?
Yeah.
Not exponentially.
Yeah. Yeah, the velocity is going to have a bigger role than the mass.
Can we do number 80?
Yep.
Yeah, we did. I think we did partial.
Yeah, we did yesterday.
We did one with both.
I think that was before.
Okay.
2-8.
Yeah, this one seems like it's trickier, but it's not as tricky as you think it is. It says, consider separate samples of 1 liter samples of helium and UF6, both at 1 atm and containing the same number of moles. What ratio for the two temperatures would produce the same root mean squared velocity? Well, let's say this. Mu RMS is equal to the square root of 3 RT over M, right? And that would be for whatever gas I want to talk about. But couldn't I also say some other gas to have the same mu RMS velocity? It would also have to be equal to mu RMS. So let's call this over here, let's call this HE, and let's call this over here UF6. Okay, so if I do that, I set these equal to each other, I'm going to have 3R 8.31 joules per Kelvin mole times T, which let's just say I throw in a temperature, because I have to start somewhere. So let's say I throw in the temperature 273 Kelvin. I can throw any temperature in there. Okay. Divided by molar mass in kilograms per mole. This would be 0.004 kilograms per mole, because it's 1 times 4 grams or 4 grams per mole. Am I good there? Okay, is equal to square root of 3R, which is 8.31 joules per Kelvin mole, times whatever T is. And I got to find out that T so I can get the ratio of that T to this number. Again, it doesn't matter what number I pick here, because it's going to be a ratio to whatever that other number is. And then the molar mass here, UF16 times 238 times 19. That was 20, that would be 120 minus 6, it's 114, and 238. 12, carry the 1, 5, 352 grams per mole. So this is going to be 0.352 kilograms per mole. Okay, so one thing I can do is I can cross out the 3's, because if I can cross out the square roots by squaring both sides, right? So I can just get rid of the square roots. I can get rid of the 3's, because when I bring the 3 over here to divide, it goes away. I can get rid of the 8.31's, because when I bring that over there, it's going to divide. And what I end up getting is 273 Kelvin. I'm going to bring this up over top, 0.352 kilograms per mole, divided by 0.004 kilograms per mole, equals T. Everybody follow that transformation I made there? Yep.
I just have a quick question. Is the U in the molar mass 238 or
238, yeah, 238.
I don't understand how you can just add a temperature into a problem.
Because it's a ratio. You know, if I remember we've talked about ratios before. If I say there's 10,000 girls and 5,000 guys, you say 2 to 1, right? The ratio, it doesn't matter, the ratio is 2 to 1, it doesn't matter what the total population is. So if I'm just saying what's the ratio of temperatures, well, I gotta pick some temperature for the one and then just see how it relates to the other.
Why'd you move?
0.352 kilograms of
If I take away the square root, then I wanna get T isolated, I gotta multiply both sides by 0.352.
Why'd you get 273?
I picked it out of the air. If I want a ratio of 2 temperatures, I got to know one of the temperatures. So you pick any temperature you pick, you're going to get the same ratio. You could pick one, and then make it a lot easier on the math too.
You got rid of the freezers by dividing both sides?
Yep.
Yep.
So if you can pick one, then why even put it in there?
Well, how can you have two unknowns
You
and
can't
get a
have
ratio,
zero temperature, since temperature is an average of energy.
right?
Zero doesn't exist.
And is that saying rules cancel out or the whole?
It technically does.
The whole thing goes away.
Mathematically,
Yep. Are you guys okay with this at this point, Ronnie?
Does it matter what side temperature is?
Not really, no, not really. Yep. Okay? All right, so T equals, what I get is, let's see, 273 times 0.352 divided by 0.004, and I get 24,024, which is crazy, right? Okay, but here's the ratio of temperatures. The ratio of T of UF6 to temperature of HE is equal to 24,024 divided by 273, or 88. That's the ratio. So you need to take the temperature of UF6 up 88 times more than helium to get the UF6 is running the same speed as the heliums.
So it would be 88 to 1?
88 to 1, sorry. That's even better. That's a tricky question, I admit.
So if we put one, it'd be the same ratio?
Yep. Yep. You get the same thing, it will come out to be 88 to 1. If you put 1 in here, this is going to come out to be 88. Okay. It's a tricky one, I give you that. But that's why we do the homework, right? You know, hopefully you learn something. Now, do I throw that on a test with never giving you a question like that? No. You know? But now that I've given you a question like this for homework, do you think it's a possibility? Sure. Hope not.
So if you were to use 1, the temperature of HE would just be 1?
Yeah, let's do it, okay? Let's say we used 1, okay? So I'm going to do everything, but I'm not going to put in this 273 right now, right? I can just ignore that because it's going to be 1, right? So I'm going to get 0.352 divided by 0.004. This comes out to be 81. I think that's a significant figures issue, that's all. But it's basically the same ballpark. Okay. Good? Bye. All right, we should look at a rate of effusion problem. We haven't looked at one of them. Good. Here's one. Okay, so this says it took 4.5 minutes for 1 liter of helium to fuse through a porous barrier. How long will it take for 1 liter of CO2 gas to fuse under identical conditions? Okay, now when we're talking diffusion, what we're going to say is rate of number 1 divided by rate of 2 is equal to the square root of the molar mass of 2 divided by square root of the molar mass of number 1. Okay? Now, what I want to find out is how long it will take. Okay? So what I'm trying to find out is a rate. So I could call rate 1. 4.5. I wouldn't call that 4.5 because I would put the rate that I'm given on the numerator. And I'd rather put it in the denominator so when I solve I get the root numerator.
Just for easier math?
Yep.
Okay.
So this would be, I would put down, this would be time for CL2. Rate 2, that would be our 4.5 minutes. Now, what I could do, and I got to be careful here. Let me be careful on something here. Okay, yeah. This is pretty tricky here. What I got to be careful of here is a rate is 1.0 liters per so many minutes. Follow me? That's a rate. the volume per time. And so this is going to be 1.0 liters per 4.5 minutes. So you notice how this is 1 over something, and that's going to be in the denominator? So we got to be careful there. Okay. And then let's see, molar mass number 1. Molar mass number 1, we're calling number 1 Cl2, right? So that's Cl 2 times 35, or 70 grams per mole. Molar mass 2, we're calling 2 the helium. Helium is 1 times 4, or 4 grams per mole. Okay, so let's get our numbers in there. So rate 1 is going to be 1.0 liters per question mark minutes over 1.0 liters per 4.5 minutes equals square root of molar mass 2, which we're calling that helium, and over square root of molar mass 1, which we're calling Cl2. So I'm just going to break down some of these numbers and take some of the square roots and get it out of the way. So, let's see, 1.0 liters per question mark minutes over 1.0 liters per 4.5 minutes equals square root of 4 is going to be 2. Square root of 70, it's going to be, say, 8.4. Okay. So how about I take 2 divided by 8.4, break that down. I get 0.238 equals 1.0 liters over question mark minutes divided by 1.0 liters over 4.5 minutes. So just do your algebra, okay? So first thing I'll do is I'll probably take this and multiply it by this. So 1 times 0.238 is going to be 0.238 liters over 4.5 minutes. And that's going to be equal to this 1.0 liters over question mark minutes. I take the reciprocal of both sides. Question, go ahead.
Why is 4.5 on rate 2 and not on rate 1?
Because I'm calling rate, I want the thing that I'm trying to solve for to be in the numerator. So I chose to call that 2 to keep this in the numerator. Oh, yes.
Just a question. You got rid of the grams per mole just because it's a fraction and they're canceled out?
Actually, that's a little more complicated. Let's look at it. Let's back up here. Okay, so the grams per mole. The reason I got rid of them is because no matter what those units come out, one's over the other. They're going to cancel. So this is actually going to be grams to the 1/2, moles to the 1/2. You know what I'm saying? If you take square root of it, you get goofy powers. Is everybody okay that I flip this over? And I say, and I probably should have put this on the other side, question mark minutes over 1.0 liters is equal to 4.5 minutes over 0.238 liters. And then if I multiply both sides by 1, the liter goes away, and I get 4.5 divided by 2.238. So they get 4.5 divided by 0.238. And I get 18.9. So question mark minutes equals 18.9 minutes. Does that answer make sense? Well, ask yourself, does it make sense? Is helium bigger or smaller than Cl2? Smaller. So it should diffuse faster. Did it diffuse faster? Well, this took 4.5 minutes. How many minutes did that take? Almost 20.
How did you get to the front of the city?
How did I get here? All I did was took this 1.0 liters times 4.5 minutes, and I multiplied it times this. So I got 0.238 over 4.5, because this times this would be 0.238 times 1 over 4.5. Ronnie?
So why was the unit, so what's the unit for this, like 0.238?
Liters. There's no unit here because these units cancel out here. You follow that?
the answer, like the first time you wrote,
There's no unit for that, because that's just this reduced, and those units would cancel each other. You have square root of grams per mole over square root of grams per mole. They're gonna cancel. Doesn't matter what they are, they're the same.
How do we get 18.9?
4.5 divided by 2.238,
Okay.
times 1.
Just similar question to what Jarrell asked. Can you go over like how you actually got the 0.238 liters?
I took this, 0.1 liter over 4.5 minutes,
Yeah,
and multiplied it times 0.238.
that's it, just to.
Yep. So the 1 times 0.238 became 0.238 liters. Denominator was 4.5.
Oh, okay, because you have to isolate the
Does
fridge.
that make sense?
Yeah.
Multiplied by the fraction. Okay. A lot of stunned silence, huh?
Yes.
Probably would have been smart to work on this last week when it was assigned. Maybe,
Indeed.
maybe. I'd say the real trick to this question, and this is a real trick, is that you got to understand a rate is a volume per time, which means your unit of time is in the denominator here. And if you don't get that, that's going to screw you up in this problem. If you don't get that, you're not. If you just put down time here, well, that's not a rate. A rate's something related to time. So you got to know your definition of what a rate is. Try and look at something else. Yeah.
Yeah, sure.
What? You're swearing like crazy. What's your problem?
Oh, sorry.
Not funny. You said O-F-O 3 times, 4 times right here when it's being recorded.
Oh.
Yeah. Real cool, huh?
Sorry.
So perhaps an orange sheet would be in order.
I do.
Use your brain. Okay. Oof. You're in trouble. Okay, here's a tricky one. A little tricky. Okay. So let's say, okay, so we have a 1 liter sample, a gas. Okay, so we have volume, 1.00 liters. By the way, let me watch time here. We go to 28. Okay, good. Temperature would be 100 degrees C, or 373 K. We've got a pressure of 600 torr. And they tell me that each are 50% by mass xenon and helium. 50% by mass. Okay. Huh. Well, one of the problems is I don't know what the masses are there. And even if I did figure out how many moles were there, I wouldn't know how many moles of each were there, because I would know how many moles are there, but it's not 50% by moles, it's 50% by mass.
Sorry, what problem?
No.
What kind of problem do you say this is?
What's that?
What kind of problem do you say this is?
This has partial pressures involved, and I think there's probably chi involved as well. So I could try and go this way and say, well, I know PV and T, I could get moles, but that gets me nowhere. Because then I have to know the total number of moles of both things, but I don't know them by mass. So what do? Well, another thing I could do is say, okay, well, let's just assume for a second that is the pressure. What if I say, okay, well, if I know they're 50% by mass, why don't I just take equal masses of each of those substances and figure out how many moles that is? Follow me? If they're 50% by mass, if I take equal masses, turn them into moles, and find out how many moles it is. Okay, so let's say I take 1 gram, I'll do it simple. 1 gram of HE and 1 gram of xenon. And I want to know how many moles is that? Well, 4 grams per 1 mole. So that's easy, that's 0.25 moles of HE. 1 mole of this, I believe, weighs 131 grams. 131. And so if I take 1 divided by 131, I get 0.0076 equals 0.0076 moles of Xe. But wait a second. If I know moles of each, what can I calculate? What? Nope. I made up the mass. Chi, mole fraction. And that's going to be however many moles you have, 0.25 moles divided by the sum, 0.25 plus 0.0076. And this one's going to be 0.0076 divided by 0.25 plus 0.0076. So I get those mole fractions.
Shouldn't they add up to 1?
And they do.
Oh, never mind. I
It's okay.
saw the 0 on the end.
No,
thought it
they
was
do.
30.
Now, if you remember, chi is equal to n1 over n total. Isn't that what we just did here? N1 over n total. But is it also equal to P1 over P total? Right? Here's P total. P total. Well, if I take P total and multiply it by chi, I'm going to get P1. If I take 0.97 times 600 torr and 0.03 times 600 torr, what do I get? 0.97 times 600. This is 582 torr. And that would be partial pressure due to helium. And 0.03 times 600, that would be equal to 18 torr. And that's the partial pressure of xenon. Got a couple seconds left. Now, yeah, about 3 minutes. I know what's going on. I know you sense it too. Right now, you guys are a little frustrated, right? Is that fair to say? And you know why you're frustrated? I imagine because you think it's my fault. You know why I'm frustrated? When was this stuff assigned?
Last week.
Last week. You know? You've had time to engage this stuff, but you're waiting for me to spoon feed you. And you need to do your homework. And when you get stuck on your homework, you need to come in for help. You need to ask questions. You need to post things. But people aren't doing that. Right? So what you're telling me, what your body language and what your actions tell me is, I'm good. I don't need your help. I'm fine. That's what your actions are showing me. But I can clearly see that that's not the way people feel, right? I can feel like you want help. Is that true? Did I plead some people to get on last night and get some help? Did so many people ask for help yesterday? 0. So you guys got a quiz tomorrow. You got to study for it. Okay, you got to do some work. Practice some problems.